gas turbine jet engine.
Hello, I'm Clayton Broussard, and I am going to be the group reporter for Group 1, and we're doing the gas turbine jet engine. So a little outline of what we'll talk about. We'll do some experimental background, what we did, some data collection that we did, and then a presentation of results and some conclusions of that. So the experimental apparatus that we're talking about right now, this is a gas turbine jet engine. It consists of a compressor, a combustion chamber, a power turbine with a thrust kind of transition deflector to a free turbine that powers a alternator generator. So a little bit about the schematics of this. So as you can see, the first turbine powers the compressor, and then it also powers the turbine 2 that will power the alternator. And as you can see, the combustion comes to the inlet, goes to the compression, goes to the combustor, which has this high pressure input, which then powers the turbine. And then that makes your flow to the turbine 2, which generates your energy. And the energy is absorbed by a dissipator on the side of the experimental apparatus. So this is our control panel. We have an on-off switch right here. We have a couple pressure gauges that monitors the fuel pressure, the oil pressure, the air pressure in the inlet, and then we also have a turbine inlet temperature monitor, RPM for the first turbine and for the second turbine, 89. 6 is just kind of, it will shut off if your parameters get out of control, and it will tell you when. And then 4 and 5, 4 is your thrust generator for the power turbine, the first one, and then 5 is the, it kind of helps the second turbine control its kind of damping frequency. So if you want to generate more RPM on the turbine, you pull it up. So for the first test, we just tested the main power turbine by just leaving the 5 switch down on the free turbine and pulling up the thrust on the 4 turbine, the thrust nozzle, which pretty much is kind of seeing the RPM of the power turbine. And then for the second test, we, as we turn on the thrust of the power turbine, we also regulate the free turbine by pulling up those switches on 4 and 5. So here's the TurboGen software that we use to calculate parameters that we need to know. There are 5 Type K thermocouples that are placed throughout the system on each individual component. You have the inlet, compressor, power turbine, and then you have your free turbine, and then your exhaust. As you can see right here, you have voltage current, a little RPM on the first power turbine. On the other side, you have your power output of the generator and your free turbine RPM. So from our data collected for the second test, I made some charts on pressure versus time and temperature versus time for each component. So this is our compressor. As you can see, our inlet pressure is almost at 0 at the beginning, and then it is compressed to a pressure of beginning around 35 kPa, and then it goes all the way up as the turbine RPM rises, and you can see your temperature kind of rises too as the pressure increases. For your power turbine, your pressure versus time, the pressure of the turbine is increased as your power is increased, and also the temperature is slowly increased due to the combustion chamber. As you can see, the temperature is very high during that combustion chamber process. So for a free turbine, the pressure kind of remains a little iffy. It kind of remains below the point. And then for a temperature, it decreases because you're putting work. The work is absorbed by the free turbine, so your temperature is decreased from, let's say, 550 degrees Celsius to around 350 because the work is taking the energy from this system. So your RPM versus time for the power turbine, as it increases, you can see that for the free turbine, we kind of wanted to get up to 800 RPM, and right when we hit 800 RPM the first time, the throttle was let go on the free turbine, which dropped it down to around 100 RPM, 1,000 RPM, and then we brought it back up to the point where we wanted to take our kind of like our parameters. So from this, I took a point around the second peak of the free turbine RPM and generated some work equations from that. So around 127 seconds during the test, I found the temperatures of each state, which was your type K thermocouples throughout the system. And then I found the entropy values from a thermodynamic textbook to generate my work, energy absorbed in the, so next slide. So this is kind of like the work I've done. I kind of took the energy absorbed specific work of each component, and then I calculated the net work from the power turbine and the thermodynamic efficiency of the power turbine, which was kind of low due to the amount of work it has to do powering the compressor and the free turbine. So this is our average power output and maximum power output of the free turbine, which was very high, which is very good for the system. And in conclusion, the thermodynamic efficiency was below average, which mainly due to just the system parameters not being somewhere to output the power. And the power turbine had negative work because it had to power a lot of different components, and the free turbine had a high power output.